We start. So we were discussing completeness. Okay. Completeness is defined as if you have any Cauchy sequence, a metric space is complete. So every Cauchy sequence has a limit in that metric space. Okay. And we have already proved that R, Rn, and L1 they are complete. We have proved it. And along the same line, after the class. Okay. So you can along the same line, you can prove that L2 is also complete. Okay. So you can is exercise. Yes. Now we do the following. S is any set. Okay. Then we define this D of S. We defined it like this. F is from S to C R or C. F is bounded. Less than C. Okay. Then we define the norm to be that is equal to norm. This is equal to norm of the F. This is a metric space with respect to this norm. So the claim is this is complete. Proof. We are going to do the same thing. So suppose Fn contained in B of S is Cauchy. That means the norm of Fn minus distance between Fn, norm of Fn minus Fm goes to 0 as n and m goes to infinity. So in particular, this means norm of Fn minus Fm infinity goes to 0. But then this is the supremum of this, right? So for fixed S in S, this is less than or equal to norm of Fn minus Fm. This is just the supremum. So this should go to 0 for each S. Okay? So this goes to 0 for each S as nm goes to 0, infinity. So this implies this is contained in real numbers, real or complex numbers. It's just a sequence in complex number. When you fix a S, okay? Fix it for any but arbitrary S. Okay? Is Cauchy. Okay. So this since C or R is complete, there exists a limit, and we call that limit as f of S. Okay, there exists a f of S in C or R. I mean, it's okay not to write like that. Either it is C or R, okay? Such that F and S converges to f of S for each S. Yes. Now we have to show that first. I mean, these are all in B of S. We have to show that this f of to show that it is actually complete. We have to show that this f new function, this function is well defined because the limit is unique. Okay, this is well defined. I mean, I think I don't have to say that. Well definedness means when you have a S, you have to unique image for that, and it should exist and it should be unique. Okay? It's a function. Okay? That's because limit is unique. Okay? There are not two limits. So now we have to show that this is a bounded function. Okay? This is in B of S, and then we have to show that this convergence is actually uniform. The convergence actually have in B of S. Then that will mean that this is actually F1 actually converges to F in the uniform topology. Okay, to show that it is bounded of S, not f of S, this is less than some m for all S. Okay, that's what we have to show. Now this is equal to, since the modulus function is continuous, you can write it like this. Okay, since modulus function is continuous, Okay, modulus function is continuous, all that. So you can write it like that. And and we know that FNS is less than, I am not writing that. You can use the same trick as in limit for all that, but this is true. Mod FNS is less than norm Fn for that. But Fn is Cauchy. We know that is Cauchy. And we know any Cauchy sequence is bounded. We have proved that Cauchy sequence is bounded. We have proved that every Cauchy sequence is bounded. That's the first thing we did. Okay, when we started discussing completeness, that's the first thing we did. So this is Cauchy. So this is bounded. So this is less than or m for all n. So the limit is also less than or equal. So this implies this is less than n. For all, limit in a second, for all s. For all s, this is true. Yes, there is no s here. So this implies is okay. This argument is okay. Instead, if you want, you can write, this is just another way of doing. You can write f of s as less than or equal to fns minus fms, plus fms. Limit. You can put the limit here if you want. You can first put f of s, and then you can write n going to infinity, the infinity. Okay, and this goes to 0 as, this will be less than or equal to norm of fn minus fm, which is Cauchy. Instead of boundedness, using the bounded, this fact, you can directly do that also. Okay, you can make this as n and m goes to infinity, this goes to 0. Okay, so for a big m, okay, this limit will also less than be epsilon. This limit, this is less than or equal to limit, n going to infinity, norm of fn minus. Okay, so this limit for a big m, this will be less than epsilon, and choose that m. For that m, this will be less than some big m. This will be bounded for each s. So that will also prove it will be less than m plus epsilon. You choose m if you want. This is another argument. That's all. Choose m. Choose m naught such that fn minus fm, this limit is less than epsilon. Okay? Here only m is the variable, the sequence variable, because you have taken the limit in n. As n and m goes to infinity, this goes to 0. So you take a big m and take n going to infinity. This will be less than epsilon. You can choose an m like that, m not like that. For that m naught, this will be bounded by c. Okay, then the whole thing will be bounded by m plus epsilon. This is another way of doing, or you can directly write like that also. Okay, I erase this because it's just another argument. Okay, now we have to prove that it actually converges in the uniform topology. For that, we have to consider this f of s minus fns. Okay, we want to consider this. The supremum of this should go to 0. That's what we have to show. Okay, now this is equal to limit, again the same thing, limit over m of fms minus fns. Okay. Right? There m is there. So I have taken there's some problem in the tongue for several days. I'm still having it, some tongue ulcer or something. So if you can't understand what I'm saying, if you're not here properly, you tell me. Okay. So this limit in this, what did I say? Yeah, this is limit in m, and then n is varying. For each n we have to show that. Or n large we have to show that this is less than epsilon. So now this fms minus fns mod is less than or equal to norm fm minus fn, and you can make this less than epsilon for m and big if you want, or you can take the limit. This limit is less than or equal to this limit over n, right? N. Again, the same argument. You can choose a big n m. Here, it should be n. Okay, here m. You can take a big n so that the limit will be less than epsilon. So that will be less than. Same argument. Okay. multiply f of s minus fns is less than epsilon for the big enough n for bpn. Okay, doesn't matter. Okay, now we have proved that b of s is complete for any set. Okay, in particular L infinity, everything is complete. Okay, okay. Now we consider a particular set. Second, so X is a metric space now. Then you consider CBX equal to all functions from X to whatever you like, CRR, which is contained in B of X of course, okay, which is all those and F is bounded. I mean, if X is compact, then it is automatically bounded. We have already seen. Okay, so otherwise we have to take only bounded continuous function. Okay, so which is contained in Bx with respect to the same norm infinity. This is complete because the following this, I mean, this is a lemma. If you want, I just write it, I don't prove it. Okay? If X not contained in X closed, then X complete implies X not complete. A closed subset of a complete metric space is complete with respect to the same restricted metric. Okay? If we have a sequence, if we have a Cauchy sequence here, that is a Cauchy sequence here. So that will have a limit here, but since it is closed, it has to be here. Okay? So closed subspace of a complete metric space is complete. Now to prove that CBX is complete, this is complete, we only have to prove that this is closed. Okay, so CBX contained in B of S is closed. That's what we have to prove that this is actually complete. And this is closed, this we have already done. First thing is, if you have a sequence here, if it converges, the limit is bounded. We have already seen. Even if you have a Cauchy sequence bounded, if you have a bounded sequence which converges uniformly, then it is bounded. Even Cauchy sequence will be bounded. That's we have proved. I mean, it will have a limit which will be bounded. And we also know that uniform limit of continuous function is continuous. Okay? So if you have a sequence which is converging, then the limit has to be here. So it's closed, right? What does closed means? We take a sequence here and it converges some f, then f has to be here. Okay? If you have a sequence here that is a continuous functions, and it convergence means in this topology means it converges uniformly. Okay? So uniform limit of continuous function is continuous, and it is also bounded. So this is closed. It has to be here and it's closed. Okay, so this is closed. Okay. Now, if you consider third example, you take C1 of 0, 1. It is I defined this in the first class, which is all those f from 0, 1 to I mean function taking values in CRR, doesn't matter, continuous, differentiable, and f prime is also continuous. Okay. So this is contained in C01, is not closed. Okay. In fact, it is dense. Okay. It is dense. Because Weierstrass theorem will tell you Weierstrass all polynomials are differentiable and all polynomials are here, and the polynomials are dense in continuous function 0. Weierstrass theorem, which you have seen. Okay. We will see more general theorem, Stone-Weierstrass theorem, we'll see. But we will be using Weierstrass theorem to prove that. Okay. So you should know Weierstrass theorem. Okay. So because of this, this is not complete. It is in fact not closed in continuous function. But we defined a different metric. Under that metric, it will be closed. Okay. So that is why, that is the reason we defined the other metric. Because it is dense. Because its closure is 0. Closed means what? The closure has to be equal to itself. Its closure is big, so it's not closed. There is a function which is here, which is not closed. There are polynomials here. Closed means sequence here should converge to something here itself. But polynomials will converge to any continuous function which is not differentiable. So it's not closed. But with respect to some other So it is not close, it is dense with respect to this infinity norm, the uniform convergence. If you have a different norm, it will be complete with respect to that. So that's what you want. So this is 3, C1, 0, 1. I mean, it is differentiable on the open interval. Okay, when I say differentiable, it's differentiable on the open interval. It's continuous on the closed interval, but when you restrict to the open interval, it is differentiable. C01 with respect to this norm, which we have already defined with respect to this norm, norm F. I put the infinity down, no? Infinity 1, okay, which is equal to norm of F infinity plus norm of F prime infinity. F prime is also a continuous function, so you can talk about this. And this is a norm. This is a norm, and this gives us a metric. And with respect to this norm is complete. So why is this true? We want to prove completeness. It is not contained in any of these B of S, okay, because the norm is different. We cannot. This is not contained in any of those things. Okay? So we have to consider Cauchy sequence now. So suppose Fn contained in C1, 0, 1 is Cauchy. Remember, it is Cauchy with respect to this norm, the new norm, okay, which is sum of infinity norm of F and infinity norm of F prime is the new norm. Is Cauchy with respect to that. That is norm of Fn minus Fm infinity plus norm of Fn prime minus Fm prime infinity goes to 0. That's what it means. Okay. In particular, this implies Fn prime, both contained in C01 as a continuous function, okay, is Cauchy as C01 with respect to the infinity norm. That's what it means. Okay. This is not one infinity norm. This is just the infinity norm, uniform convergence. Okay. So there exists a Fg in C01. Remember, we will get F and G such that Fn converges to F uniformly and Fn prime converges to G uniformly. Have you seen any theorem? F1 converges to F uniformly. Okay. That is in this norm, infinity. So can you say anything? Have you seen something? If Fn converges to F uniformly, Fn prime converges to G, some G uniformly, what can you say? F prime should be equal to G. You know this theorem? It needs little bit work. You use mean value theorem, it will follow. You can prove it. It takes some time. But if you haven't seen it in the first course, analysis 1, you haven't seen it. Okay, so I will ask someone to give a proof of this. Okay, that it's not difficult, but let's not do it now. Also, because of that, this implies F prime equal to G. So how did you say? If you don't know, haven't seen a proof, how did you say? You just I mean, when you don't have a proof, when you haven't seen a proof, how can you say something? We guessed it. Okay, so this is true. Okay, so now you know that this thing also, so this implies Fn minus F1 infinity converges to 0. Okay, so complete. That's the statement. So the statement is C101 is complete with respect to that new norm. Okay. Now, okay, I give an assignment. Next assignment. So, to define C0 to be all sequences 0. And you take C, which is all xn. Xn is converges, xn converges. You take, this is a space of all sequence converging to 0. This is a space of all convergent sequences. All convergent sequences are bounded. So all these things are contained in L infinity. Okay. We have already proved L infinity is complete because B of S is complete. Here S is natural number. Okay, L infinity is bounded sequences in natural numbers. I mean, it's B of n. Okay, L infinity is nothing but B of the n, according to our notation. So this is complete. So your assignment is to prove that these things are complete. Okay. So you have to prove, take a sequence xn. Assume, I mean, you take a sequence of sequences. Okay. You take a sequence here, xm bar or xk bar or something, or here you have xk, whatever. You take a sequence of sequences. If it converges in this infinity norm, L infinity norm, you will have a limit, of course, because I mean, if it is Cauchy and other thing, you will have a limit because you have proved that it's, so it has a limit. You have to prove that that limit is there. That sequence should also converge to 0. Once you prove this, this is easy because this C is nothing but, I'll erase this, C direct sum complex numbers as a vector space. What it means the following: if you take any convergent sequence, okay, then you take this. If you have a convergent sequence, then the limit is x. Suppose the limit is x. You consider x1 minus x. This sequence will converge to 0. Subtract the limit, that will go to 0. Okay, so this will look like xn minus x plus constant sequence x. Okay. C here means it's not C. If you take any complex number or real number, I mean, it depends on which vector space you take. Okay, complex or real. This is one dimensional. Here, this is not C means not just one. I mean, not just C. This is actually C, right? As a vector space, this is just C. You take all constant sequences. That is isomorphic to C, right? As a vector space. Okay. So this is C is like this, and this sequence converges to 0. Okay, you can use that fact to prove that this is, or you can directly prove also. Okay. That's the assignment. So let us see some consequence of completeness now. So we will be using this theorem also. We have already seen this kind of things. So the proof is very easy, very direct. This has a name. Contour spelling is correct, no? C-A? C-O or C-A? C-A, no? Intersection theorem. Contour intersection theorem. So the theorem is follows. It's important that X is complete. You have a complete metric space. X is a complete metric space. And you have a sequence Fn of subsets, decreasing sequence of closed subsets. That is, Fn's are closed and it is decreasing. That is, Fn plus 1 is contained in Fn. Okay? Like this. Okay? That's what it is decreasing. Okay? Decreasing sequence of closed subsets. There are closed subsets. Okay? Such that the diameter, did I define diameter? Then I will write it. Diameter of Fn goes to 0. Okay? Then let me write the statement and then define diameter. Then intersection of all these Fn n equal to 1 to infinity is singleton. For it's non-empty and it has one element for some x in x. Okay. The diameter is just the maximum distance. Diameter of any set A is equal to supremum of dxy. Okay, xy is the diameter. Diameter of an open ball is 2r. dxr is 2r. Okay. So if you have a decreasing sequence of closed subset, more or less it's clear, no? You have a decreasing sequence of closed subset and which and its diameter is also decreasing, okay, then it should have only one element, provided X is complete. Okay. There are too many assumptions. We have already seen this while proving something about compactness. Something implies something. We had this situation. We indeed use the directly the proof of this. We didn't have it as a theorem. We used completeness. We almost proved. We almost used that. I'm just going to repeat proof. And we prove totally boundedness and complete implies sequentially compact. Further, we used it. Okay. So the proof is I mean the first claim is first claim is that if X and Y are in intersection of n equal to 1 to infinity Fn, okay, then X and Y are in Fn for all of, right? X and Y are in the intersection means it is in all n. So it is in Fn. So this should be less than diameter of Fn, which goes to 0. There is no n here. So this implies dxy equal to 0. So this implies x equal to y. The property of metric. This implies x equal to y. So there is only one element. If at all there is an element, there is only one element. Now we have to prove it's non-empty. Okay. So to prove non-empty, choose xn in Fn. Okay, then dxn xm. So Fn's are decreasing. So if m is greater than n, m is greater than n, we can assume one of them will be greater than the other. So the d of xn xm is less than or equal to diameter of xn, the smallest one. I mean, xn, m is greater than n, so xn xm both will be in Fn. Okay, so it should be less than the diameter of Fn, which goes to 0. I mean, there is no m here. As m is greater than m, so it has to that should also goes to. So as nm goes to infinity, this goes to 0. Okay. So this is Cauchy. So this implies you just arbitrarily choose an element that is Cauchy. Since X is complete, implies Xn converges to X. Okay. Now this X has to be in Fn for all the elements, right? I mean, that is because Xn is a sequence. If you consider this sequence, Xn, n equal to m to infinity. Okay. This is something contained in Fm, right? After this, it has to be in Fm, right? Fm. Okay. And this sequence converges to X. Since Fn is closed, it has to be in that. So since Fm is closed, X is in Fm for all M. Okay, so this is the kind of intersection theorem. Would be very trivial. Just wrote all the arguments. That's all. Okay. So since we are discussing diameter, this is not related to completeness. You don't need completeness. But since it involves diameter, I prove another interesting fact. If you have an, the X need not be complete. Okay, X is some metric space. You have an need not be closed. There is nothing about an contained in X. Okay, and I am not assuming it is need not be decreasing or anything. Okay? There is nothing is assumed. Just I am assuming diameter of AN goes to 0. I think there is nothing else needed. Okay? Diameter of AN goes to 0, and it's important, intersection of AN 1 to infinity is non-empty. Okay? Of course, the same argument, if the diameter goes to 0, there cannot be more than one element. It has to be singleton by the same argument. Okay? So it will be only one element. Okay? So then what? So now suppose suppose f is a function. F is function from x to y, continuous. Okay? Then diameter of f of AN also goes to 0. That is the statement. Okay? The diameter of AN goes to 0, and intersection is non-empty. There is nothing else is assumed. Okay, intersection is non-empty, and diameter AN goes to 0. Then f is continuous. F takes this kind of sets to this kind of sets. F of AN also goes to 0, and it's of course will be clear that f of x is equal to intersection f of AN. Okay. Proof. So why is this true? So since the diameter, this is non-empty, we already proved that it has to be only one element, and that is this. Okay, n equal to 1 to infinity AN. Okay, there is nothing assumed about decreasing or anything. It is just the intersection is non-empty, so it has to be some singleton. Okay. Now, since f is continuous, given epsilon greater than 0, for some arbitrary epsilon greater than 0, choose delta greater than 0 such that dyx is less than delta implies d of f of y, f of x is less than epsilon. Okay. This is we are doing for this x. We are using the continuity at x. Okay. Okay. Now choose n naught, okay, such that diameter AN goes to 0, okay, such that diameter of AN is less than delta for all n greater than or equal to n naught. Because we are assuming diameter AN goes to 0. So this is possible. Okay. So for y in AN, dxy is less than delta for all n greater than or equal to n naught. This implies d of f of x, f of y is less than epsilon. Yeah, f of x, f of x is the center, f of y is less than epsilon for all y in AN, for all n greater than n naught. Epsilon is arbitrary. So this implies, this says, what this says is the following. X is the center, okay? This implies diameter. Y is in, x is, f of x is somewhere, but y is in f of AN. Sorry, f of y is in f of AN. Y is in AN, so f of y is A. So diameter of AN is less than 2 epsilon for all n greater than n naught. So this goes to 0. This means this goes to, exactly. Diameter f of AN. Yeah. goes to 0. This means it goes to 0. That's what we want to prove. And it is clear f of x has to be that. Right? X is there, then f of x is there in all of them, f of x will be there in all of them. So that's okay. Yeah, incidentally, this is not true if that assumption is not counterexamined. If not true, proposition not true. If intersection an equal to empty, I mean intersection an equal to empty, then the diameter an goes to 0. Doesn't mean f of f is continuous. Doesn't mean f of an will go to, I mean diameter f of an will go to 0. So example is take an, take x equal to this whole thing, and an equal to, and y equal to 0 infinity, x equal to 0, 0, 1. Here it's open. I mean, compact sets will be bounded. So in compactness it will work, but I'm taking, so a non-compact set, and y is 1 to infinity. An equal to 0, 1 by n. Open is enough. Open is okay. Open, close, it doesn't matter. We are worried about only diameter. Okay. And define f from x to y by f of x equal to 1 by x. Then f of an equal to n infinity, and the diameter is infinity. I mean, infinity cannot go to 0. Sequence of infinity cannot go to 0. You don't like this infinity. You want to be a finite one. Then you take f of x. So take g of x equal to sine of 1 by x. Okay. Because this will land up, 1 by x will land up in n infinity. This will certainly contain an interval n 2n 2 pi 2n pi plus 2n plus 1 pi, 2n plus 2 pi, whatever. Okay, it will have something. So this image will be g of an will be minus 1 1 for all n. Because the diameter is 2, it will not go to 0. So this will not work when the intersection is empty. So this is a digression from completeness. It's not about completeness. Now we want to, so we'll come back to completeness. So if you want to write, you stop me. If you are writing or something, you ask me to wait before I start the new talk. Some spaces may not be complete, but it can be embedded into it can sit as a dense subspace of a complete metric space. So that is what is called completion. It's like taking a closure, but closure you will take inside a metric space. I mean, it's a well-defined metric space. It is with respect to that. This is an abstract one. You get another metric space where this is embedded inside. Okay. So what it means by embedding? First I want to. So embedding is the following. So definition. You have a function show xy metric spaces. I don't know whether I defined earlier. A d from x to y, not f from x to y is isometry if d of f of x, it preserves the metric, that's all, is equal to d of xy. If it preserves the metric, then it's called isometry. Okay, this is for all xy. And it's clearly continuous. Okay? Isometry implies continuous because given epsilon, you have to choose a delta, choose epsilon equal to delta, that's all. Okay, it will work. And it's 1 1. It's injective truths. It's injective because if f of x equal to f of y, that means d of f of x, d of f of y equals 0. So d of x y should be 0. So x equal to y. It's clear. So injective is clear. So that's all. It need not be onto, of course. You can embed anything into anything. I mean, you can take the identity map. Some A is contained in some X. You can just take the identity map inside that. I mean, so that's isometry, of course, but it's not onto. It need not be onto. So an embedding, you call an isometry from, I mean, an isometry. Usually, between matrix spaces, we consider homeomorphism. But homeomorphism is just F is continuous, F inverse continuous, F is bijective. It need not preserve the distance. If it preserves the distance also, then it's called isometry. If it is, of course, an isometry which is onto is a homeomorphism also. And F inverse will also be continuous. Clear. So an isometry from X to Y, X inside Y, it need not be onto, is an embedding. It need not be surjective. It's called embedding. So a completion of a metric space, definition. X is some metric space. Okay. If I write X bar, it may be confusing. So X tilde, X is a metric space. X tilde is a completion, is a completion, I say. So there may be more completions. There may not be one completion. It's a completion of X if X tilde is complete to start with. And there exists an embedding of X2. I call it, I may be phi from X to X tilde. Okay. An isometry, an embedding such that this phi of X is dense. Okay. Phi of X closure equal to X tilde. Phi of X is dense in X tilde. So you can embed this metric space into a bigger metric space so that it is dense there. It sits as a dense subspace. Okay, that's what the completion is. Okay. So the proposition is the following. There exists a completion of it for any metric space. Usually what one will do is, you have a metric space and you take all Cauchy sequences, just sequences. You take the set of all Cauchy sequences and you embed this X into that set of all Cauchy sequence as constant. Okay. You take X tilde. This is not what I'm going to do. I'm just telling you. Either some TA will present this to you, or you will write it as assignment. You will see. I'll give you the argument. X tilde is all Cauchy sequences in X. Okay. Then you can, for any X, you can write this constant sequence X. This also Cauchy. That will sit inside X tilde like that. On that X tilde, you define a metric. You can just consider this d of X and yn. If you have two Cauchy sequence, you consider this. This will have a limit, and that limit will be a metric. Okay. With respect to this, it will be a complete metric space, and there this will sit as dense subspace. Okay. So this will be a completion. This is one completion. Okay. For some reason, I am giving you some different proof. Okay. So there exists a completion for any metric space. Further, maybe after this, I will prove it as the next proposition. Okay. because the completion is unique, I want to say. Unique up to isometric. That is, if we have two completions, x tilde and y tilde, then there is a bijective isometric. I mean, that is x tilde and y tilde are homeomorphic. Further, the homeomorphism is actually in isometric. They are isometrically homeomorphic. Okay. Isometrically isomorphic, one can say, but here we use the word homeomorphic. So there exists a completion for any metric space. Proof. For x fix. What we will do is the following. We take any x in x. We want to embed into a metric space. That metric space will be this completely bounded functions in x, which we have already did. I mean, no, not completely bounded, sorry. Continuous and bounded functions. It's completely bounded is somewhere else in the back behind and then coming. So, which is a concept in operator algebra. So, this is continuously bounded. All functions which are continuous and it is bounded. Okay? We will embed this x into this. By the way, I mean, you have already seen those functions. Okay? So, but then for x in x, define fx at y equal to, of course, dxy. You know, this is a continuous function. This is the first continuous function we saw. If we have any metric space, then this is a continuous function, and this is actually the one. I mean, if you have the question whether continuous function exists on a metric space, this is the first continuous function we see. That the power automatically comes. So these are all continuous functions, but these continuous functions may not be bounded. But we want bounded functions. In bounded functions only, we have that norm, supremum norm. So to make it bounded, I will do something. Slightly change the function. Okay. So I'm not going to take fxy. This is continuous function, we know, but this may not be bounded, right? Fxy, the distance is not infinite, but it can blow up to infinity. Okay? So the diameter of, if it is compact or if the diameter of x is not finite, then it can blow. If x is not a bounded, the metric is not bounded. If you have a bounded metric, this will work. This itself works, same proof will work. So if it's not bounded, define fx at y equal to, and you choose, I mean, for x, I'm defining fx and fixing this a for all functions. Okay, such that this is dxy minus dy. And d, if you fix for any y, the y going to dxy is a continuous function. We have already seen. Indeed, it's uniformly continuous. Similarly, y going to dy is also uniformly continuous. So the difference is also continuous. Okay, so there is no problem. And we want to prove that, so this is continuous. So we have fx then x is where fx is in continuous functions in x. Okay, for all x. So this is the embedding we want to say. Okay. So first we have fx is continuous. Right? Bounded we have to prove. It follows and it's clear. So fx is continuous. Fx is continuous. And to prove bounded, mod of fxy we want to consider, which is equal to mod of dxy minus dy. Of course, this is less than or equal to, we know that dAx, dxa. For each x, the y is not there, this is for all y. So this implies fx is bounded and it is already continuous, so this is in CDI. Okay. The thing is, it's very direct, what we do is direct. And we already know this is a complete metric space. Okay. This is contained in B of x and it is It's closed in B of X and it's complete. Okay, we already seen that's the first thing is. Okay. So now what do we have to do? We have proved that, and we have proved that it is continuous function and all that. We have to prove that it's an actually an isometric. Is there anything else we have to prove? Yeah. So it's continuous and it is bounded. Now we have to prove it's isometric. So for that you can compute the norm fx. What is it norm? Okay, we have to come fx infinity. Okay, no. So we have this. We have this. And if you fx at x, you just see what is fx at x. Fx at x is going to be, this is 0, and the fdax. Okay. Yeah, fx at x is dax. Okay, yeah. So fx at x is dax. So the supremum is attained at x. Okay. dax. So the supremum is attained. So this implies norm of fx infinity, which is just the supremum of fxy. Okay, fxy is less than dxa, we have proved, and at fx x is dax. So this should be equal to dax. Okay, for all x. But we want to consider this d of f of x, d of f of x f of y, which is equal to norm of fx minus fy infinity. Okay, that is equal to, well, let's just write it. That is equal to 4 terms will be there. Mod of d of x. Let me write z, sorry, because y is a variable we want to consider. So z d of xy minus d of ax, ay, minus of that. So this will be minus d of zy plus d of ay, right? And the whole mod of this, right? I just the difference. So this implies, so what is this? This is less than or equal to, of course, you can triangle inequality, d of xy minus d of a, d of ay and ay, that will cancel. So this is just d of zy. So that is less than or equal to d of xz, right? So this implies the same argument, fx minus fy is less than or equal to dxz. That's the statement, this infinity now. Okay. On the other hand, fx at z, fx at z. Okay. If you take at z, it is going to be just dxz, right? Dxz. This will be 0. Dx is equal to dxz. So this implies d of fx fy, which is equal to norm of fx minus fy infinity is equal to dxz. So this implies this map phi of x going to fx. This is a map. Phi is a map from x into cbx. Okay, is isometric. Okay, it's isometric, and but its closure is not cbx. For a completion, you have to take the closure. The closure will be p P of X contained in the CBX. You have to take this P of X. This is a metric space with respect to which is closed. Sorry, P of X closure. You have to take the closure. Sorry. To take the closure, this need not be everything. You call this as X tilde. Okay? Is the completion. We have embedded X into that. Just take the closure inside a completion plane, which is complete. So that is the completion. So there exists a completion. That's what we have to do. It's very easy. Unnecessarily, I wrote all that. I mean, I just spelled out everything. Now, the next proposition is the completion is unique. Unique. That is, let me write it in the proof. Okay. Suppose unique up to isometry. If you have two completion, by whatever the definition, then there is an exists an isometry between them, which is bijection. So that's what it means. That is if X tilde, Y tilde are two completions, then there exists a theta from X tilde to Y tilde isometry, a bijection. Isometry implies it is continuous. Because if something is an isometry, inverse is also isometry, so everything is continuous, and it is bijection also. I mean, it's surjective. That's all. Isometry is automatically 1, 1. So here it's surjective also. The proof is direct. Theta 1 from X into X tilde, but not this. So if we have two completions and theta 2 from X to Y tilde are two completions, I mean two isometries. Okay. Such that their image is dense there. That's the definition of a completion. You just write down the definition, everything, you will get it. So such that theta 1 of X is dense in X tilde and theta 2 of X is dense in Y tilde. Y tilde, there's no Y tilde, it's okay. Y tilde. Okay. So then theta 2 of theta 1 inverse is a map from theta 1 of X to theta 2 of X, right? And it's an isometric isometry and it's onto bijective isometry, right? It's onto because theta t ranges it theta 1 inverse will bring to X and theta 2 will act on that will be theta 2 X. Okay? So it's clear. It's a isometry and it's also onto. Okay? And isometry implies what? Uniformly continuous. Okay. If you so the assignment, there is an assignment. Have we done it? If you have a uniformly continuous function defined on a dense subset, then you can extend to the closure. Okay? Uniquely. Okay? So there exists a theta from, and it will also be isometric if you want, because there is a this from X tilde to Y tilde, an isometry such that theta restricted to whatever that theta 1x equal to theta 2, theta 1 inverse. Okay, whatever that. This is an isometry defined on a dense subspace. This is dense here. Okay, this theta 1 is dense in X delta. Okay, now because it's uniformly continuous, you can extend it to a uniformly continuous function. That will be isometry. This is isometry since metric is continuous, right? If xn converges to x, yn converges to y, then dxn yn will converge to dxy, right? Okay. So if that is how the map is extended, you will take a sequence here in this, and then you define to the, I mean, and that will be well defined. All those things you have to verify. Okay, then that's how it is defined. Okay, so this preserves the distance d of x and y, and that preserves the distance means this will also preserve the distance. Yeah, of course. What is the definition of uniform continuity? You have to choose the epsilon equal to delta in that continuity statement. Uniform continuity is you can choose the delta uniformly. Epsilon equal to delta for all so uniformly continuous. It's direct, it's trivial. By definition, it follows. So something is isometry on a dense subspace when you extend it continuously. Okay, that's also isometry, right? Because exercise. Okay, convince yourself. Write down the proof. That's also isometric. Means something here will be a sequence here, and another one yn y. If you have xy here, there will be xn converging to here, yn converging to here. So this theta of x and theta of yn, that distance is same as t of theta of d of x and yn. So d of theta of xy will be the same as, d of xy will be same as d of theta of x, theta y. Okay, so it's also an isometry. And further, there is one more thing. The image of an closed set is closed under isometry. Further, this is a lemma. And theta of x tilde will be equal to y tilde. Since, let me write the statement and show it to you. Since image of isometry, image of closed set under isometry is closed. Why is it true? Proof. So if you have an isometry, theta from x tilde to y tilde, isometry. Okay. Then suppose yn converges to y. This is happening inside y tilde. Okay. Or if you have theta of yn, theta of yn converges to some z. Okay, this is contained in y tilde and this is in y. You have to prove that z is also an element. But then since it is an isometry, okay, theta of y, that will also be Cauchy. I mean, theta inverse is also an isometry, right? So yn is Cauchy, theta inverse of theta of yn equal to yn is Cauchy. Because isometry preserves the distance means Cauchiness is preserved. Okay, is Cauchy. This is recording. I am not making a political statement. So this is also Cauchy. So since that x tilde is complete, yn will converge to y. Now theta of yn will converge to theta of y. That's what we want. Okay, so this is equal to z, right? So this is in theta of x tilde. So image of a closed set under isometry is closed. Okay. So you have got everything now. And theta and the rate, this range is dense there, so it has to be surjective, right? Already this map theta takes this theta 1x to the image of x here, theta 2x. Okay, so that will be closed. I mean, that will be dense there. So it is closed means it has to be surjective. So we have proved that this theta is an isometry, surjective isometry. Okay. Any question? If you have questions, tell me in the next class.